Oh, no, still.
Yes, sir. Yes, sir.
We can start.
Yeah, we were talking about permanent magnet, synchronous motor type of AC motor. It construction yesterday we just started, correct? Very simple. It is synchronous motor, but rotor is a permanent magnet. So lot of complications are reduced. Supplying power, DC power, slip ring. Due to that, complicated mechanical weight reduction. All this thing is advantages. And then there are two types of coil windings, or the stator coil winding. One is called distributed winding, other one is called concentrated winding. And we saw that. Then when we talked about rotors also, then excitation. Excitation also going to be sinusoidal or trapezoidal. Back EMF generated depends upon the coil distribution. Please note that how the coils are wound. The stator coil, whether they are distributed evenly in sinusoidal patient or in trapezoidal patient. Accordingly, the back EMF generated in the stator by the rotor. Rotor is rotating, permanent magnet, correct? It is rotating. Because of flux induced by the rotor, which is cut by the stator coil, there will be a back EMF. That back EMF shape will be whether it is sinusoidal or trapezoidal. That's what this figure shows. That depends upon how the stator coils are distributed or wound. If it is wound sinusoidally, correct? Then the EMF, back EMF generated in the stator coil by the rotor magnet will be this one. Of course, you are going to supply a AC voltage to the stator coil. That voltage will be sinusoidal, correct? In the PMSM, it will be sinusoidal. If it is this one, trapezoidal, other model. Okay, so that we talked about the advantage. We talked about it. Salient pole motor will have projections. We already I show yesterday. Yeah. So if the magnets are projecting outside, correct? So this is called as salient pole, correct? This we can see here. The rotor core on which magnet is attached on the top of this one, but it is projecting. This is called salient pole. You can see that no projection outside. Magnet is buried inside the rotor core. Or here, magnet is put over the core, but the magnet size almost covers most of the surface except small gaps. So again, if you see here, this almost look like a smooth surface, correct? So then we have two types. One is called surface mounted. These four are magnets are mounted. Black color is the magnet. The gray color is the core, rotor core, on which the magnets are called surface mounted magnet. This gives evenly distributed magnetic flux between the stator and rotor. The gap will be this one. That is over this one. Because of that, the torque generated will be smooth. All those things. Advantages are already told you. Other one is called interior. In the interior, this one you can see the core is circular, cylindrical shape, no projection. The magnet are buried inside this, and you can see that there are two types. This is called interior IPM, short form interior permanent magnet rotor. Correct. In the interior permanent magnet is inside. These are surface mounted. First top row, the all four are surface mounted. Here these two also surface mounted. The lines you can see the black color lines. So these are called magnetic flux, because you know that permanent magnet north and south pole. For example, this is north pole where I am showing arrow. This is south pole. Again, this is south pole. This is north pole. Again, this is south pole, north pole. There are four magnets. So the magnetic flux created by the north pole. Okay, I can show it. This one you can understand that. Created. This is the north pole. Is attracted by south pole of this magnet. Again, north pole of this magnet. Because this is one magnet. This is second magnet. Third, fourth. All four magnets are mounted on the surface of the rotor core. Correct? These are called surface mounted because these are all called surface mounted, including these two. Okay, because magnet are mounted on the surface of the rotor. Rotor is a magnetic material, right? Made of magnetic material. These are permanent magnets. Permanent magnet made of rare earth magnets. Correct? Already we saw what are the rare earth magnets. We have very high this one. Then you can see that the magnetic flux from north goes to south. This north goes to this south, like this. The flux distribution, right? These lines are flux distribution lines, correct? Between two pole pairs is happening. Again, same thing is there. How the magnets are there, depending upon that, the magnetic flux distribution happens. But these all 6 shapes are shown as surface mounted rotor. Magnets are mounted on the surface of this one. Okay, these 2 are called interior mounted magnets. Already that is mentioned clearly. Okay, you can see that in this there are 2 types. There one is this is magnet, this is magnet, this is black color core, and you can see that magnetic flux can cross couple like this between 2 magnets. Correct. In order to avoid that, sometimes they put what you call as spacers, non-magnetic spacers. The white square blocks are called non-magnetic spacers, which prevent short circuiting of the magnetic wave between the magnets. Correct? Between the magnets, the magnetic flux cannot travel. Between these 2, it can travel. Between these 2, it can travel. Because there is no separator. These 4 are called as magnetic separators, made of non-magnetic magnetic separators. It has some advantage because each one, see each shape, how the magnets mount, interior, all this thing has some advantage. You can see it if you want more detail later, because we have limited time. We are trying to understand what are different type of motors used in electric hybrid vehicle, because we need to cover a lot of syllabus. Okay, so again, one more thing also we saw that depending upon the LD and LQ, whether LD equal to LQ or LD is smaller than LQ or LD is greater than, correct, LQ. Based on that, what you call a saliency of rotor. Okay, that is another important parameter. That is ratio between the LD and LQ. LD is called as inductance in direct axis. I will show that. That is LD. LQ is inductance at quadrature axis. Okay, so that is depending upon that. Again, we say saliency. Saliency is another important parameter which decides how the torque is produced in permanent magnet synchronous motor. Correct. For more detail, you can look into books. Okay. That's what here I want to say. Rotor saliency is the variation in the inductance of rotor in D axis and X axis. D is called direct axis. Q is called a quadrature axis. The other name for rotor saliency is called magnetic saliency or inductance saliency. Okay. That is shown here. If I shown a picture, no. Yeah, you can see here. This picture, this is my rotor. Rotor is a single, this one, it has a north and south pole, and stator has A, B, C. There are 3 phases. 3-phase AC voltage we are giving is supplied to stator coil. Correct. There are 3 coils in which the AC voltage applied. We are applying AC voltage, which is 120-degree separated, and with 3-phase. Then we have a rotor. Rotor has a not correct. This is a permanent magnet. The stator coil produces electromagnetic rotating magnetic field. Okay, that is what that will attract this magnet, because you can think that this can be think as a magnet. Correct, north and south pole. This will be get locked. Correct. We know that this produces rotating magnetic flux. Correct. So this is called MMF, magnetic flux generated by 3-phase coil. Okay. So resultant magnetic. This will be north. Sorry, this is south. North means this will get locked. Similarly, here you will have resultant magnetic flux. So when the magnetic flux rotates, this one, the rotor is magnetically locked, both north and south pole. It also rotates. That's how torque is produced. Okay, we know that it is similar to synchronous motor. Only thing is here you have permanent magnet. So the direct axis means we know that this is the magnet. Correct. I told you the rotor magnet. This axis, the center part. Correct. Let me clear it. You can see it. Right. So you can see that this is the center axis of the rotor magnet, north and south pole. In the center, if I draw a line aligning in the center of north and pole connecting a projected, that is called a direct axis. Okay, exactly 90 degree to this axis called quadrature. Quadrature means 90 degree. In the trigonometry, all this things, say quadrature angle means 90 degree. With respect to the rotor magnetic axis, which is called direct axis, that is nothing but the line connecting north and south pole of the rotor. Correct? The center line. That is called quadrature angle. So if you measure inductance, correct, electromagnetic inductance with respect to Q axis, it is called LQ. Inductance with respect to quadrature angle. Similarly, LD means inductance measured with respect to D axis of the rotor. That is called LD, LQ. These are all called as two inductance value of the synchronous motor with respect to axis. Design torque production, smoothness, how much a torque produces in the permanent magnet synchronous motor. That's why they have different types of rotors. How the magnets are put over the rotor, fixed over the rotor, correct? Please see that the magnets will be bolted. There may be screws and bolted strongly because this is going to rotate. It will generate centrifugal force. The magnets will not come out. That is one of the drawbacks. Please note that I already told you. One of the drawback of the surface mounted. Correct. This is the surface mounted. This time there are 4. Correct. These 4 are the RPM of the rotor increases. If motor speed more 2,000, 3,000, 4,000, the centrifugal force, correct? Centrifugal force is outward force generated with respect to shaft axis will be very high and the magnets can fly away. That's why the surface mounted, this one, SPM they called is PM SM motor, subcategory SPM, surface permanent magnet motor, means the magnets are mounted on the surface of the rotor. These motor will not be generally run at high speed. High speed operation, generally low speed. Low speed is not 100, 200 RPM. It can go 2,000, 3,000 RPM, but not 10,000 to 8,000. They are low speed operation and their efficient low speed operation. If a higher speed going to because you are going to fix the these magnets using some nut or bolt studs, correct? So that you have to fix it. You cannot glue it like using a araldite, something like that. You have to fix with this. Even with that, if force can it come out, large centrifugal force. In that case, if you are going to run your permanent synchronous higher speed, you have to select the interior IPM motor. Magnet are buried inside this. It cannot come out. Correct? You can see that magnet got almost entirely buried deep inside the rotor core. They can go, IPM motors can run at a higher speed also. It can run from lower to higher speed also. But the torque production is less here compared to the surface mounted for the same size. So these are the parameters when you select a motor, you have to really think about it. Already we saw that. I wanted to explain what the LD ratio, correct. Already we talked about LD ratio frequently. We will talk about this one. The rotor saliency depends upon LQ divided by L1. LQ divided by LD. Correct. LQ is the quadrature inductance. LD is the direct induction, direct axis induction. If this is greater than 1, then rotor has higher saliency. Better performance will be there. Correct? It has a better performance. Rotor saliency is greater than 1. That means LQ divided by LD is greater than 1. That kind of motor provide better performance. Okay. So that also you have to note down. So again, now we will talk about how this works. Okay, permanent monitor, because we know that we are going to supply. There are 3 coils, correct? A, B, C. A coil, this is the current is entering here, current is coming out, 1 coil. Similarly, B coil, current is entering, current is coming out. Similarly, C coil, current is entering, current is coming out. Of course, the coil wound out inside the stator surface. That is, you have slots in the slot. This is the core of this stator core. Inside that, you have slots in which the wires, 3 sets of wires are wound over it. There we call the stator windings. It will be supplied with 3 voltage. I call say VA, VB, or VC. Some books I say red phase, blue phase, green phase, 3 phase voltage. It depends upon. Here we can take it VA, VB, VC, correct? Because we have 3 coils, each one is supplied. Now, since you are supplying this one voltage to each coil, there is a resultant magnetic flux, of magnetic flux created by the voltage supplied to the stator. So that stator axis, correct? Each coil produce a magnetic flux. Each one is 180-degree separated. You know that voltage also 180 degrees separated in spatially. We see the
120
coils
na,
also.
sir.
Yes,
Sir,
please.
120 degree, na?
Sir, excellent. Thank you. Kind of you. Very good. Thank you very much. It is 120 degree because the 3 phase totally 360. Okay. So the voltage, current, VA, VB, VC, IA, IB, IC, and similarly we say B. Here we are talking as AS, BS, and CS. These are the magnetic flux axis, MMF axis, correct? They are also separated by 120 degree. You can see here. CS axis here, BS is here, AS. If you measure this angle, it will be 120 degree between 3. 120, 120. The coils also, rotor, stator coils also spatially separated 120 degree. Voltage applied also 120 degree. Current and magnetic, all those things. With respect to that, you have the, so 3 are the stator magnetic flux angles, separate 120 degree. You have a permanent magnet, but the permanent magnet also produces its own magnetic flux. There are 2 magnets. One is called magnetic flux at the direct axis. That is the axis between following the south and north pole of the rotor magnet. It is a result. And with respect to same axis, there's another magnetic flux is there, which is called a quadrature magnetic axis. So that is 90 degree. That is called quadrature. We will do this. Correct? This is what is mentioned here. Okay. Now, how the torque is produced, we wanted to understand. So you can see that phase A, phase B, phase 3, we are supplying VA, VB, VC voltages. Okay, we have put capital A. We can use same terminology. Okay, so because of that, there's a current flowing inside each coil. Correct? IA, IB, IC. Please note that the stator coils are made of copper wires. It has resistance, but theoretically, many times I told you, at least many times, the coil. Theoretical coil, if I say coil, L means just inductance alone is there. Correct? Theoretical inductance or pure inductance, we call it. Pure or theoretical inductance will have just inductance. What is unit of inductance? Henries. I can say the L equal to Henries. Okay, L equal to 10 H or L equal to 0.1 H or L equal to 0.001 H. Correct? Milli-Henries, micro-Henries, something, correct? Or Henries. So, but this is theoretical. But practical, you have a wire, you take a copper wire and you make it as a coil. So, copper wire has cross-sectional area A, it has resistivity rho, and it has a length L. Correct? You took 1 meter wire, made it as a coil with having a area. Correct? I am talking about coil area, having some cross-sectional diameter, and coil also has a length. Then you can calculate inductance. Inductance is proportional to capital A and the length of the coil, and also the psi, permeability of the core material. Here the air is there. We saw the sequent mechatronic. I'm not going to repeat it. So this is for theoretical inductance. But since I took a copper wire, copper already has a resistance. Correct? It is not a superconductor. So that means each phase of the coil has resistance Rs, that is stator subscript S means stator coil resistance and stator coil inductance. This is for phase A. Similarly, Rs, all those things. And there's a current flowing. Correct? You can say that current IA equal to VA divided by root of Rs square plus XL square. Okay. Where XL equal to, already we know the 2 pi F into Ls, where F is the frequency of supply, L is the inductance of this inductance. Okay. So this is called as, can be called as a Z. I can write that IA equal to VA divided by Z, where Z equal to root of Rs square plus X square, I can say. Correct? X square is nothing but Ls, this one the formula. Okay. So because you supplied 3-phase coil with 3 voltages. Okay. 3 voltages. There are 3 currents. Once because there is a magnetic flux is created. There's a magnetic flux is created. Already we call MMF. Apart from that, you can see here there is another EMA. EMA are called back EMFs. Back EMF induced in the rotor coil. Sorry, stator coil. Induced in the stator coil due to flux from rotor. Rotor is a permanent magnet. It is rotating. That flux will be cut by this coil. These coils are cut because of there is a voltage. That is called back EMF. That back EMF is also in series with the supplied voltage. Please see that we have applied VA, VB, VC. VA equal to, this is called input voltage. According to KVL, Kirchhoff's voltage law, applied voltage equal to voltage drop across the coil due to the current flowing plus the back EMF for this one. That's what it is. VA should be equal to Rs, this current, this resistance into this current IA, that is the voltage across this. Similarly, this current multiplied by that is rate of change in inductance, the voltage equal to inductance value multiplied by d by dt of current flow. Rate of change, this one. So this is inductive voltage. I say VLS, I can say VRS. These two plus this is back EMF generated by this one. So the equation according to KVL for each phase, we have 3 phase means 3 voltage equation we written. Okay, for phase A, phase B, phase C. Where what is the EMA back EMF? We know that back EMF already we talked about motors. In mechatronics also I talked about it. When we talked about DC motor, I told you back EMF is induced in a coil when the coil cuts another magnetic flux. The rotor magnetic flux are cut. So that is proportional to omega, where omega is rotor speed. Omega is rotor speed. Correct? And Ka, Kb, Kc are called as back EMF constant. Note down. It is called as back EMF constant. Correct? So back EMF constant will be same. Maybe 0.1, 0.5. I don't know any some number. Correct? So that will be given by motor manufacturer. One that is known, please note that the back EMF is not constant. Omega is going to change from 0 to say 5,000. Right? What is omega? Or omega is nothing but rotor speed, shaft speed. When you apply initially correct voltage at t equals 0, rotor is under this one. Correct? Stationary condition. That time omega is 0. For example, I take for understanding this is equal to 5. 5 into 0, automatically it will be 0 volts. The back EMF voltage, the back EMF also measured at volts. The voltage by back EMF is 0 because the omega is 0. But as motor start rotating, speed increases 0, 10 RPM, 20 RPM, it goes up to this one. So you will multiply, you see that back EMF will start increasing. Correct? This EMF will increase with respect to omega. 0 to, for example, I say that 5,000. So this will increase like this. As the omega increases, the back EMF is 0 to, for example, 100 volts something. Applying, say, for example, 200 volts for a AC voltage with peak value, back EMF. We know that already I told you the current IA, current IA is nothing but supply voltage, that is V voltage minus back EMF voltage divided by Z. That is what IA. In AC motors, the voltage applied minus the induced back EMF. Or AC or DC motors it happens wherever the back EMF is generated. Supply voltage minus back EMF divided by Z will be the current flowing at any given time. What will be the current at T equal to 0 when rotor is not rotating? You just apply the voltage, rotor yet to start because the magnetic flux has just get produced. So that the interaction is there. What will be this one? The IA will be maximum. Why? Because back EMF is 0. This is 200 volts minus 0 divided by Z equal to 10. I say 200 divided by 10, 20 amps current will begin. So that's why you see in motors, starting current will be very high. As motors start increasing, speed start increasing, the back EMF increases. For example, after 10 seconds, my back EMF becomes say 50 volts. That means 200 minus 50 divided by my Z is going to be same. Correct? My Z is going to become frequency same, automatically bigger 10. That means 150 divided by 10, 15 amps current. So at the full speed, for example, when motor reaches 1000 RPM, for example, that time the back EMF equal to say 150. Correct? 200 minus 150 divided by 10 is going to be 5 amps current. So at 1000 RPM, the motor will take only 5 amps current. Correct? The proportional power is consumed and the proportional mechanical power is generated in the shaft. Already we talked about electrical power equal to V into I, mechanical power equal to omega into T, where omega is the shaft speed, T is the torque produced in the shaft. This is input, this is my output. Output power in the motor will be always lesser than input because already we saw many losses: copper loss, windage losses, air gap losses, right? And also core losses. We saw that already previous class we saw. Okay. So now that you know this equation, please note down this equivalent circuit called equivalent circuit of stator. Equivalent circuit of stator. Stator winding, three-phase stator winding. Okay. So this is voltage, these equations in the exam it is expected. Okay. So now, because you supplied this one, the rotating magnetic field is created because of this magnetic 3 voltage applied, current is flowing. It generates as phi A, phi B, and phi C. And this is being three phase, it is going to the phi R. Already we talked about synchronous motor, how the induction motor already shows how at the given angle, correct? The voltage is varying sinusoidally in 3 phases at theta equal to 0 degree, theta equal to 60 degree, theta equal to 180 degree. And we are calculated because it is going to create rotating magnetic fields. That is called resultant magnet. This magnetic flux only going to get locked with the stator, correct? Rotor magnet. I say that phi rotor, correct? Small r, right? So these two will get locked and this is rotating. So the rotor also rotating. That's how it works. So please note down this. So now we know that there are 2 types of rotors in permanent magnet synchronous motor. One is called as the salient pole. Other one is non-salient pole. Another one also we talked about it. We know that the induced voltage in the stator can be sinusoidal, correct? Back EMF induced in the stator and also the supply voltage. Supply voltage also will be sinusoidal voltage, AC sinusoidal. The back EMF generated induced in the stator coil by the rotating rotor will be sinusoidal. We are talking of sinusoidal back EMF. This correct? So that depends upon the distribution of the stator coil winding, whether it is concentrated winding or What is the other one? We just talked, just to do. We talked two type of windings. Uniformly distributed winding one type, other one is concentrated winding. In uniformly distributed winding, we will supply AC sinusoidal voltage in the stator coil. We are talking about stator coil. So it produces a magnetic which is also sinusoidal. Apart from that, you have a permanent magnet which you are rotating. Initially, you rotate synchronous motor. You have to rotate this one so that it cuts the stator coils, and in stator coil a back EMF is produced. The back EMF will be sinusoidal in shape if it is uniformly distributed. Correct. So if that is shown, if you have, we know the two type of windings. There are stator. With uniform distributed, you supply AC voltage sinusoidal, and the magnetic flux generated, back EMF generated also will be sinusoidal like this. Okay. We are talking about electrical angle is shown here. In that case, we are deriving the equation for the rotor, correct? So rotor d by dt of id, correct? What is I? I is the current flowing, correct? I is the current flowing with respect to the quadrature angle. If I say I, sorry, the direct angle, IQ means quadrature angle, correct? Please note that in the take down this equation, all the parameters are explained here. Note down. D by dt id equal to 1 by LD, is the inductance in direct axis multiplied by voltage induced in the direction VD. Correct? Voltage in the D axis. Then R divided by LD into ID plus LQ divided by LD into P into omega M into IQ. IQ is because all the parameters explained here, where P is called number of poles, correct? Number of pole pair, correct? Number of pole pair talks P. When if the problem is given, you will given the pole or pole pair, correct? Pole or pole pairs are given. So this is the, because we know that in the synchronous motor rotor, there are two inductors, two currents are flowing. One is called ID, other one is IQ. Okay, d by dt of IQ equal to 1 divided by LQ into VQ minus R divided by LQ to IQ minus L divided by LQ into P to omega minus another term is that. Please see that this term comes in, correct? So this is quadrature, correct? This is the quadrature angle. Now, for this motor, once this is known, correct, we can find out torque developed. Torque produced, take the equation, torque produced by the motor, okay, in which the magnetic the coil is distributed evenly, correct? Stator windings are distributed evenly. It is stator winding excited by the sinusoidal AC voltage, three-phase sinusoidal voltage. Then the torque generated in that motor can be written as TE, motor torque generated equal to, actually it is 3 by 2. There are many books, you will see that this term will represent by 3 by 2 into P into bracket lambda multiply IQ plus LD minus LQ into ID into IQ, where ID, IQ are current in direct axis, current in quadrature axis. Okay. Lambda is called amplitude of magnetic flux induced by permanent magnet, the rotor of the in the stator phases. Correct. This is the magnetic flux amplitude which is generated. This is induced by the rotor magnet. Correct. Rotor is rotating. That magnetic flux is cut by the stator winding. Stator winding is stationary. Please note that according to Faraday's law, whether magnetic flux are changing or wire is moving, you have constant magnetic flux north and south. Magnetic flux are like this. Many times I told you, okay, and the magnet is not moving, fixed. I take a wire and move the wire inside the, for example, diagonally. This wire is moving like this. This is my wire is moving in this direction. Right? So then your voltage EMF will be generated in this wire. This is what generator. Generator means you have a magnetic flux in which wire is, a copper wire is cutting the magnetic flux. Then a voltage. This is what electrical generator. Okay. Instead of that, I have magnetic flux. Okay. And I pass voltage. in the this one, plus minus, there's a current flowing. Magnetic flux, that I am supplying current. Automatically, again, one more magnetic flux is created due to current flow in the wire. So then this magnetic flux interacts with the already existing magnetic flux. This we call as a field magnet or stator magnet. This is called a rotor magnet or armature magnet. So there are two magnets, they interact, the force is created. So since the stator or field, the permanent magnet is in the body, it can coil is not moving. The wire which is attached in the rotor or armature and it is allowed to rotate. So the force is able to make the rotor to rotate, and the actual force is generated by interaction between the magnetic field by the current flowing in the coil or armature or rotor coil, which will interact with stator magnetic field. So, force, this is how this works. So, you can note down this. So, the torque equation is this, where LQ, LR, inductor, represent relative phase angle. Already we know that. So, you again, some more detailed information is available, correct? This is the final equation. There's a derivation is available. You need not worry about this. So, this part you can ignore right now. Okay, so this you need to note down this equation, and this is a torque. Okay, this is for one type of rotor. Okay, one type of rotor with one type of motor. Correct. Distributed winding. The back EMF generated by the rotor in the stator field is sinusoidal nature, because the windings are wound sinusoidally or evenly distributed in the stator, and you are supplying with the sinusoidal AC voltage. Instead of that, you can give, you have a winding which is concentrated winding, and you are supplying the stator winding with the trapezoidal waveform. This is called a trapezoidal waveform. So, correct? The shape is trapezoidal, is not a sinusoidal like this. Okay. If the waveform, that is what we are talking is, we are talking about the voltage supplied to stator winding is trapezoidal, three-phase trapezoidal sine wave, and the back EMF generated by the rotor magnet in the stator field also in the same shape, so that they can then only. Please note that if the voltage supplied to stator is sinusoidal, the back EMF generated by the rotor magnet also should be sinusoidal. Then only they will sync with each other, and the maximum torque motor will work efficiently. Okay. So if the voltage applied to the stator coil is trapezoidal, for which you apply the concentrated winding motor only, you will supply trapezoidal voltage. No doubt, right? You will in case synchronous. So the induced voltage. In that case, again you have the equation. Note down the equation in the d by dt of IA, correct? D by dt, rate of change of current in the IA, IB, and IC, correct? It will be written like this. The torque equation is this. The torque equation is this. Okay. So, where the parameters are explained. IA, IB is the phase current due to the voltage supplied by the trapezoidal waveform. Phi A, phi B, phi C dash dash means the electromagnetic force created in the stator field, correct, due to the magnetic flux supplied. Lambda is the magnetic flux supplied by the rotor. Rotor is only one magnet, correct? That magnet is rotating. That flux density decides what will be the magnetic flux created, back EMF, all these things. And we see that voltage between A and B coil and also B and C coil is represented AB AC, correct? AB AC phase voltages. In this equation, wherever you are seeing AB AC, this VAB, VB means the voltage between, we have three voltages, VA, VB, VC. correct? Between the two phase voltage, they are called phase voltages. Then omega m is the angular velocity of the rotor or shaft angle or motor speed. And lambda is the amplitude of magnetic flux generated by the permanent magnet of the rotor in the stator field. P is the pole pair. T is the electromagnetic torque. So you can see that if the trapezoidal magnetic voltage is applied and the back EMF generator also this one, because the coils are concentrated winding, then torque equation slightly varies. Note on this torque equation. Okay. So here what we are talking is, we know that the motor, correct? The acceleration, d by dt of omega m. Omega m is the motor shaft speed, correct? So d by dt omega m is nothing but acceleration. Shaft acceleration is nothing but 1 divided by j into Te. T is the torque generated by the electromagnet, this one. This is called induced torque, correct? Tau induced, previous class we saw, correct? Induction motor, we saw that tau induced, here it is Te, or torque generated by electromagnetic force or interaction between stator and rotor. But this torque is generated, this all the torque is not going to come out in the shaft. Shaft torque is always less because of the other losses, correct? So it's nothing to TF is called frictional torque, correct? And also you can see that F into omega m, correct? F into omega m is the this one varies with respect to motor speed. If motor speed increases, this much, these are losses. And this is so mechanical losses, correct? So all these things are shown here. So the final equation can be written like this, equated, correct? So the acceleration is 1 divided by j. J is called the rotor inertia. Rotor has a mass, it has an inertia. 1 divided by inertia of the rotor multiplied by Te minus Tf minus T, this one is the acceleration of the motor. Okay, whereby d by dt of omega can be written as omega m. In this case, omega m equal to nothing but omega d by dt, where theta is nothing but d by dt of theta. Theta is an angular displacement of shaft. Correct? Angular displacement, you differentiate, you will get the velocity, angular velocity. If you differentiate angular velocity by this one, you will get this. Okay, now that we saw this, and now please note down comparison of different type of.
Sir, if you can go to the previous slides, I'm sorry to ask one question. So this basically this T expression, the P lambda into phi dash A or it's like phi A only? It's
Phi A dash.
Phi A dash, okay.
Rate of change of flux.
Right, sir, I got the
flux
point.
It is not a constant flux, it is varying flux.
Correct? Perfect, sir.
Because you are applying your time varying voltage, so the flux also now will be vary like this only. It is not a constant flux.
Right, and secondly, this dot is a vector multiplication or is a just a square multiplication with IA?
Where
this dot Te, P lambda.
It is vector multiplication. It is not vector quantity, no?
So phase will come in the picture, right?
Yes.
Okay, sir, fine. Thank you.
Okay. Now that we saw two type of rotors, please take down this one. What is the advantage of what type of permanent magnet you will select? Whether you select exterior. Exterior called, other name is surface mounted. Surface mounted rotor is called as exterior rotor, because magnet are fixed on the surface, exterior of the rotor core. So they are surface mounted, also called as exterior, otherwise interior type. Correct? Magnet are buried inside rotor core. So advantage. This is simple construction. This is relatively, because the manufacturing, but really complicated your construction. Because you can see that you have to make a slot inside, correct? This is complicated, no? Compared, this is just to bolt it. These are the exterior. Exteriors, fixing is simple. Rotor, you can make the stud or screw and fix it, all those things. But here in the, you have to cut a slot inside the core and insert the magnet. Complicated process. This is complicated. That's what we have. Interior type rotor fabrication is, construction is little complicated compared to exterior type. And that means production, manufacturing cost, all those things. That's what we are talking here. Then air gap flux density, correct? Air gap density is constant. Okay. Here, air gap magnetic density is smaller than BR and then BR. Here constant magnetic flux, but here the air gap will be smaller between the rotor, correct, and the stator. The gap between these two will be this one, and I think something I missed. Okay, I will tell you. It cannot be BR. I will tell you. No, we'll not do that. Then the armature, small armature reaction flux. Okay, because the magnetic flux is distributed smoothly. In case surface mounted, the magnetic flux is distributed in the air gap smoothly between the armature rotor and also the stator coil. So because of the flux reaction will be very small. Here the reaction between the armature reaction flux is higher. Then rotor permanent magnet is not protected armature field. Correct. Please note that another thing also I just want to tell you. In some books, the stator winding they call it as armature. Please note that if you refer some books in permanent, this one armature field is nothing but a stator. Because I saw in one of the yesterday some books while just going through, sometimes they rotor they say, other one, please know the armature we talk only in DC motors. But in the PM SM also, some books, the stator field winding is called as armature field. Okay. So the rotor permanent max not protected against the armature field or stator field, and here protected because the magnets, and we talked about it. If I remember correctly, this you can say stator. You can write it as stator field. We need not get confused. Okay. Again, I told you, if you remember just another 5 minutes, when we talked about it, rotors, just a minute.
29.
with an 156 because flow का directly proportional रहता है compression ratio
Just
का
Okay. Please see that in parameter this one, the flux density is same. Another thing, the problem with the surface mounted, correct, is the magnets. Air gap between the stator winding and the rotor are very small. Because of that, the magnets, which magnet? The rotor magnets, these magnets will be cutting the stator magnetic flux. If you being very close, okay, then what will happen if the magnet itself is a conducting, correct? Because the permanent magnet can be made with highly conducting material, correct? If the highly conducting material, correct, electrically conducting, that's what I mentioned. Please see here, if the electrically conducting, if the rotor magnets, permanent magnets are made of electrically conducting materials, then if this rotor magnets are cutting the stator magnetic field because they're very close, because the outer surface, then it will induce another eddy current, volt current inside the magnet. Which magnet? The permanent magnets of the rotor. So because of the eddy current generated inside that, heat is generated. If you know that magnet, if you heat, please note that permanent magnet should not be taken near the heat. If hot surface you take a permanent bar magnet, it will lose its magnetic. If you heat a permanent magnet, correct, it loses its magnetic flux depending on how long you expose, what is the heat, higher the temperature. So that is another drawback of surface mounted rotor. One of the drawback, because these magnets are exposed to field magnetic flux, rotating magnetic flux, because of there's a voltage induced inside the magnet. This is already the magnetic flux. It is not an electromagnet, but since it is made of highly conducting material, which is used for making this permanent magnet, then if it cuts the magnetic flux of the stator magnetic flux, definitely going to cut. Because it's very close, then there will be a heat is produced due to eddy and all those things. Then the rotor magnet will lose its magnetic power. Correct? So if he loses, we know that torque produced is proportional to the rotor magnetic field and the stator magnetic field. Correct? So if the magnetic field is getting reduced, please note the permanent magnet, because of heat, continuous exposure of this one, and then what will happen? It will lose its magnet, then torque production motor. Initially, for example, we bought a surface mounted motor, permanent magnet synchronous motor. Say, for example, they say that 500 watts, or for example, for your vehicle, correct? Say 50 kilowatts, torque is say 150 Newton meter or 200 Newton meter, correct? For first few days, as it becomes longer. And another thing, this electrical losses is created, or magnetic power loss created in the permanent magnet is directly related to the RPM of the rotor. If motor rotates higher speed, more magnetic flux will be cut by the rotor magnets, more eddy current, more heat. The magnet will lose its magnetic flux quickly, permanent magnet. Then the torque produced by your motor will result. After a few years, you say that you give a warranty for your vehicle, correct? Permanent magnet based, that is surface mounted rotor, you are using 100 kilowatt motor, for example, 200 Newton meter torque. Okay, you said that 5-year warranty, correct? But if the motor is designed for running at high speed, correct? So then it can lose its magnetic flux. These are the points when taking designing motor, vehicle design. What type of motor you have to select, you have to design. That's what I'm explaining all these things. Okay, so that is one thing. Low permanent magnetic flux leakage, here it is higher if you use interior type. Poor magnetic weakening capability. That means, as I told, if you run at high speed, the magnetic weakening will be more. Quickly, the permanent will lose. That is why you have to run this motor up to medium speed. Correct? 0 to 2000 RPM, 0 to 3000 RPM. That is what this kind of motor. If the rotor is made of surface mounted rotor or exterior type rotor, the motor design, manufacturer will say that the RPM will be 3000 RPM. Maximum speed it can achieve. But because of these reasons. But if you use interior, higher speed is possible. Magnet is protected. Correct? Magnet is inside the core. So the magnetic stator coil is not going to generate eddy current inside your rotor magnet because it is buried inside the core. So it is protected. So large flux weakening capability because rotor will absorb a lot of the faculty, not magnet. Higher flux with this one, then higher speed is possible because the magnets are not affected. You can run your motor at higher speed. Okay, I think I will stop here. Okay, so yeah, well, just 2 slides. I want to close it. Torque control in the permanent magnet, there are 2 types. One is called sinusoidal category, other one called trapezoidal category. That depends upon winding. Correct? That means we are talking about sinusoidally excited stator coil which are evenly distributed or distributed winding supplied with sinusoidal waveform for stator coil, and the rotor also produces a back EMF because the distributed coil is there. The induced back EMF also will be sinusoidal because evenly distributes. In that case, if your coils are excited or permanent magnet motor, excited sinusoidal this one, sinusoidal back EMF. You have 3 types of motor control, speed control. One is called scalar type, other called vector field type, FOC, field oriented control. Third one is called direct torque control. If it is a trapezoidal category, voltage applied to trapezoidal, we saw that. That means concentrated winding. You are supplying your trapezoidal excitation A, B, C. VA, VB, VC is not sinusoidal to stator. It's a trapezoidal waveform, as I told you here. Right? Like this. The input voltage supplied to 3-phase coil of the stator. The winding is a concentrated, not distributed winding. Then the back EMF generated by the rotor in the concentrated coil also will be same as this trapezoidal. They will interact each other, they produce. Okay. In that case, you will be using open loop control to produce a trapezoidal voltage. you use open through wheel control and closed through. The two type controls are there. We are not going to deeper into that. These are the techniques available, correct? So three type of control techniques: sinusoidal, trapezoidal. There are two open loop, closed loop type. Okay. Then last slide for today. We know the permanent magnetic synchronous motor can work also as a generator, correct? So, for example, when no load condition, the stator magnetic field is rotating with the NS, correct? My rotor, there's no load, no friction. I think theoretical rotor having zero mass, correct? Mass of the rotor is zero. That means it is able to run with no friction, no inertial, this one J, correct? Inertial load. So that means it is able to catch up NR. You can also say NS equal to NR. That is no load condition. But I told you in practical, definitely not possible. But NR will be close to NS will be equal to NR. Practical no load condition. Then you can see that both the magnetic flux of the all are aligned. Magnetic fields of the stator phi S is aligned with phi R, same axis. Correct? There are two, this one. Now, this is still motor, but the zero load. Now, if it start loading the rotor, correct? Apply load, you can see that this is NS. NS is moving forward. NR is trying to capture. This is NR, this is NS. So, rotating magnetic field is higher. That means this is greater than NR. That means you can see that this is trying to catch. The magnetic flux will be linked. This is magnetic locking, correct? Magnet is locked. I am talking with the arrows. The rotor is trying to catch the stator, but still it is lagging. This is the axis, this is the axis. There is a phase angle, correct? The small phase angle is there between these two, correct? So in that case, we say that the motor TMS SM machine is working as a motor. I can, when I want to recover, correct, energy during braking, regenerative braking, what will happen? The same motor, you cannot have two devices, correct? The motor will become a generator. That will, at that time, what will happen? The rotor will be running higher than, greater than NS, correct? That means the rotor moves, it induces voltage, flux. That flux will induce a voltage in the stator coil. That voltage is you are going to convert and store in the battery. So at that time, your motor works as a generator. In this case, rotor speed is faster than, rotor is driven by wheel, correct? Wheel is driving, and the stator, you are not applying voltage. The magnetic flux, the rotor is cut by the stator field, and it generates voltage, AC voltage, that will be converted DC voltage by rectifier circuit, and your battery will be charged. So that's what we are talking. So that means permanent synchronous machine can work as a motor as well as the generator, depending upon whether rotor is trying to catch up with the rotating magnetic field or rotor is moving ahead of the magnetic field. That's what I have to say. And I stop here. Thank you. We'll see on Monday. Okay. Thank you. Have a nice weekend. Please give your attendance before leaving.
Thank you, sir. Put the attendance.
Yeah, I am not. I'll wait for 2 minutes. You can give your attendance and go.